let's start with okay. You know, water is life. So, every drop of water is very important in our nature, and nature makes everything to protect each and every drop of water. And we have in the tear film several mechanisms to protect our water. In back to 1946, Eugene Wolf described the three layer of tear films, and afterwards, in the way that he described the tear films was an anatomical presentation. It was the mucin layer, aqueous layer, and lipid layer, as if they are not interacting with each other. But now, as we move forward, now with the deuce 2 and deuce 3, if you look at those, there is a continuum and there's an interaction between those layers. So we define like a dynamic integrated system in which the lipid layer, the mucoaqueous gel, and the underlying epithelium forms a continuous physiochemical interface rather than a discrete strata, so that those layers penetrate, cross-regulate, communicate at cellular, molecular, and mechanical levels. Let's see the details. Now, this is the tear layer, and you see the lipid layer has all the cholesterol, fatty acids, triglycerides at the outermost layer. The important thing is how they adhere to the aqueous layers just beneath it, that has the water, lysozyme, many immunoglobulins, and magnesium, sodium, all those elements. And then the mucin layer has the hyaluronic acid and the mucins that are either secreted or they are attached to the glycocalyx, so that they can hold all the tear film over the corneal epithelium. So we have an intact, nicely operating wet ocular surface. Let's start from the mucin. It's rather than the coating, it's a way to communicate. So that's we have found in these years. So the mucins are high molecular weight glycoproteins, mostly carbohydrates. They are negatively charged and highly hydrophilic, so that they can hold on to the tears, to the aqueous layer. And this allows them to hold water, resist dehydration, and serve as a bridge between the epithelium and the tear film. And let's see the functional structure of these are the glycocalyx that you are watching here. There are two kinds of mucins, which are the membrane bound and the secretory ones. The membrane bound ones are anchored to the epithelial membranes and form those glycocalyx, and they extend to the surface. And this extension has several meanings, like they prevent the microbial adhesion and also transmit the signals. So this is important. This is something new. So they transmit signals so that telling the cells that the surface is dry, there is bacteria on the surface, there is something abnormal. So this transduction is important, and this is a newly defined function of the membrane associated mucus. And there are secretory mucus. They are secreted to the surface. They are not bound to anywhere, and they have a viscoelastic gel so that they can hold the liquid layer and provide hydration. Now let's go to the aqueous domain. So it's rather than a passive filler, it's a bioactive medium. It is secreted from the lacrimal glands, and it has electrolytes like sodium potassium chloride. It has like over 6 species of proteins, and lactoferrin, lysozyme, and lipocalin. We will come to that. This is very important. Although it's in the mucoaqueous layer, it holds the lipids, so it's important. We have the peptides, we have the vitamins, we have the cytokines. So it's a very rich in nutrients. And so we are now referring the mucoaqueous layer as a continuum. So we are not having like 3 layers, we are now having 2 layers of the tear film. The aqueous layer interpenetrates the mucin network, so there is no discrete border. And together they form a hydrated gel system so that they can retain water. And it is bioactive, and it has reflex to the osmotic and inflammatory changes. So it reacts according to it sends signals to the lacrimal gland that it needs more hydration. And coming to the lipid layer, we know that it regulates evaporation and has a function of the surface tension, and it provides a smooth optical surface and prevents contamination by dust and the pathogens. So it functions as a biophysical stabilizer responding to blinking and temperature changes. These are important because when there is absence of these mechanisms, or if there's a problem, we constitute the artificial tears according to that. So let's see the tear film. Here is the tear film. We have the polar, and I think it doesn't work here. Anyway, it has this one. So this is the tear film. So we have the nonpolar and polar. This structure, the nonpolar is 95% and polars are 5%. The nonpolars are the whole bulk of the lipid layer and have the cholesterol esters, wax esters, and it provides the optical smoothness. But the polar lipids, which are amphipathic, which means they have a phobic and a philic domain so that they can hold to the lipid layer. These are very important and acts as a surfactant, and it helps the cohesion of the liquid layer. The most important parts, now we have artificial tears which have phospholipid, is the trace phospholipids. They are so minor and they are not at the layers. They are bound to the mucoaqueous layer and they hold with the lipocalin, they hold the whole lipid layer. So this is very important. So it means that when we have an evaporative tear film deficiency, we are also looking for problems at the mucoaqueous layer. So we can supplement the tears according to that. So the classical view says that if we have a thick lipid layer, we can protect the evaporation. But the studies show that you need to put a high amount of lipids to protect the evaporation. But a small amount of phospholipids, which are bound to the lipocalins, are helping to get to prevent the evaporation and having a stable lipid layer. So it also comes to how much we need to put the lipid-containing aqueous, lipid-containing artificial drops and replacing those phospholipids. So when we come to DUCE-3, which is recently published, that lipid layer is not independent and lipocalins in the mucoaqueous layer bind meibomian lipids and they help to distribute those lipids. And the lipid film relies on the mucin conditioning gel, and evaporation or instability reflects interface failures, not lipid deficiency alone. So this is an important message here. So when we look at the classical view, rather than static, we have a dynamic tear, and there's an interdependent continuum here. Now, the primary function, rather than lubrication and protection, we have the barrier, signal, and mechanical integrated system. And rather than the anatomical entities, there's functional domain, and the focus of deficiency is not the deficiency of one layer, it's rather the dysregulation of the system and imbalance. And it's not just a tear film, of course. We are talking about the ocular system and the tear film. So the lacrimal gland, the meibomian, the conjunctiva, all are included in our ocular surface disease system. So everything's interacts with each other. And not limited to that, there's a lacrimal functional unit we have. So it connects to the nervous system, to the brain, also the immunity system, the lymphatics and circulations, and all of them are altogether the lacrimal functional unit. So when there is dryness, when there is cooling at the surface receptors are triggered. Those triggers go to the trigeminal nerve and comes with the parasympathetic nerves, with the lacrimal, goblet and conjunctival cells. So the mucin, lipid, and aqueous is secreted. So nothing is doing on its own, but all are interconnected. So we started with the tear film, but end up with the lacrimal functional unit, which regulates the production, delivery, and clearance of tears to maintain a homeostatic environment on the ocular surface. I thank you for your attention.
Thank you so much, Ozlem. The next presentation in the first part of our first session is the pathophysiology of ocular surface disease, a molecular and immunological perspective. Please, Dr. Muhammad Alilu from